All right. So you're trying to solve this using Laplace transforms. How do you do Laplace transform of y double prime? It's two derivatives translate to s squared, right? S squared, capital Y of s, minus s times small y of 0, minus y prime of 0.
Is this on the sheet you just gave us?
Yeah, actually, it's in 36 if you're looking at this.
Nice.
And then, so that's what you get. And then this one is 8 times s of ys and then minus small y of 0. Okay, that's also on the sheet. It's 35 if you're interested. And then plus 25 capital Y S. And then on the right side, 13 e to the negative st. So you look at the table and look for that one. It's in number 2, right? It's 1 over s minus a, so it's s minus negative 2. So that's your Laplace transform if you apply Laplace transform both sides. Okay, now let's collect capital Y of s's. So this is s squared, and there's another one, 8 times s times ys. And then there's 25. And then y of 0 is negative 1, so we should plug in negative 1 here. Negative times negative is positive, so it's positive s. Y prime of 0 is negative 18. Y of 0 is negative 1, so that's plus 1 plus 8. And everything is accounted for. On the right side, it's 13 over s plus 2. Okay? So y of 0 is negative 1. Negative of negative 1 is positive 1. 1 times 8 is 8. That's where I got this 8.
Where did you get that? The 1 over s minus negative d.
Oh, this is in the Laplace table. It says e to the 18 is 1 over s minus a. It's in the table that you see.
Why is a negative 2?
Oh, it says here negative 2, right? All right, so you put that there. Okay, now, so the Laplace transform turns a differential equation into an algebraic equation so that we don't have to worry about differential equations anymore. So let's try to solve for ys. Let's see, s squared plus 8s plus 25 ys. Move the s to the other side, so it's negative s. Negative 18 plus 8 is negative 10. Moving to the other side is positive 10. Okay, and plus 13 over s plus 2. And then you divide this over to the other side, giving you y of s equals to negative s plus 10 is divided by s squared plus 8s plus 25. And plus 13 over s plus 2 times s squared plus 8s plus 25. Okay, so both terms are divided by s squared plus 8s plus 25. Now, it's possible to make this into a single fraction, but it's not necessary, so we're not going to do it that way, right? Again, I repeat, some books ask you to put this together as a single fraction, make this into over s plus 2 by multiplying s plus 2 top and bottom, and then combine. Actually, that's not necessary. You'll find it that later. Okay. So now we found out the solution in the form of y of s. This is Laplace transformed one. It's not the original function y of t. So how do you go back? That's the problem, right? And the method was to use the partial fraction expansion, right? Okay, so you have to write this into partial fraction expansion. So any denominator that you see, parts of it should be here. So I see s plus 2, so I put s plus 2 and put what? A. Okay. And then I see another one, which is s squared plus 8s plus 25. And you put what?
B.
No, it's a quadratic one. bs plus c. You need a first order if it's a second order. So that's how you do partial fractions. This is how it's described in most of the textbooks. However, I still need to tell you yet another trick. So rather than, if you do it like this, then afterward, even after finding A and B and C, you will still suffer trying to figure out what to do with these numbers. So it won't be this. And actually, you have to change a little bit from here.
Wait,
So
how'd you know that you had to do that again?
Oh, if it's quadratic, then you put one less, one order less.
Yeah, and then that would be right, and then why are you switching it now?
You just know?
No, it's just you can do it like this, but later on you'll suffer if you do it this way. So I'm giving you a shortcut. Okay, there's a shortcut here that you have to know.
Alright.
So what's the shortcut? The shortcut is that you first have to complete the square for the denominator. So what do you get if you complete the square? How do you complete the square? Take half of 8, right? So what's that? S plus 4 squared. And you ask yourself, 4 squared plus what gives you 25? 9, right? 4 squared is 16. 16 plus 9 gives you 25. So you put 3 here, 9 here. And then once you transform the denominator into the completed squared form, then on the top, instead of writing down bs plus c, you're going to write b times s plus 4. Whatever you get inside the square, that's going to be here. And then you're going to put a c.
What happened with the s plus 2?
Where is it? Oh, s plus 2 is here.
No, the s plus 2 under the other one.
Yeah, this will become this. You're trying to split this into 2, right? What's partial fraction expansion? You're trying to split a single fraction into sum of multiple fractions. So I'm trying to rewrite this into sum of this and that. Now you may be worried about this. What about this? Well, this can be also written in this form, right? So once I split this into these two forms, and this can also be in this form, so I can add them, and at the end it's going to be transformed into this form. Partial fraction expansion. Yes.
You would just replace the s in the first one with the s plus 4, right?
Yeah. Are you guys totally new to this partial fraction expansion thing? Do you want me to?
Please.
Okay. Really short short guide to partial fraction expansion. Okay. So if you do 1 over s minus 1 over s plus 1. Suppose you have these two fractions. This is totally unrelated to this. I'm just pulling up a new example. Can you put this into a single fraction? You can, right? How do you do that? You multiply s plus 1 to top and bottom for the first one. So it's s plus 1 over s times s plus 1 for the first one. For the second fraction, you multiply s top and bottom. So it's s over s times s plus 1. Now, since you have common denominators, you can put these two fractions into 1. So you get s plus 1 minus s, which is 1, over s times s plus 1. Okay, that's how you take two different fractions into 1, right? Now, the problem is when you have to do solve some problems using these, sometimes you have to go backwards. the first case you needed something like this was when you had to do the integration. So if you had to integrate this with ds, then this is hard to integrate. So what do? You make this into that form and integrate this instead. That's easy to integrate because that's 1 over s is ln of s. So it's ln of s minus ln of s plus 1. So that's what you did in calculus 2 when you did integration. Now here, in the context of Laplace transform, trying to find the Laplace inverse of this is hard, but trying to find the Laplace inverse of these are easy. The Laplace inverse of this is 1. Laplace inverse of this is e to the negative t. So that's really easy to figure out, whereas this is hard. So you somehow have to go back to that form. Now how do you do that? Well, so it's like this. Suppose this is what you're given, and you want to know what it is. What are the two fractions that was combined to get this one? Right? That's basically what partial fraction expansion is, right? And what you're doing is, well, for this to be the common denominator, one of the fraction must have been something over s, and the other fraction must have been something over s plus 1, right? And then you say, okay, now what about what goes on here? Well, you don't know. So you just put A, you just put B, and you just put plus, and you just hope for the best. See if you can figure out what A and B are. Okay. Now, I know that you only need A and B because this is a fraction where the order of the top is lower than the order of the bottom. So even for this, you just need the top to have order 1 less than the bottom. And since this is first order polynomial for s, this just needs a constant term. Constant term is considered a 0th order polynomial. This is a first order polynomial. So the order of the top is less than the bottom. Okay? So as long as you keep that rule, then you know that this can be written in this form. Okay? And actually we do know the answer. A has to be 1 and B has to be negative 1. But the question is, how can we find out that A is 1 and B is negative 1 if we didn't know this? Okay? And that's basically what partial fraction expansion is, right? Now, how do you actually find A and B? There are many methods, but the one that I like is to multiply this both sides, so you get 1 equals to, what would you get on the right side if you do that? A over s times this is what? If you multiply this to this fraction, s and s will cancel, leaving you with s plus 1, right? So it'll be A times s plus 1. And then if you have b over s plus 1 times this thing, s plus 1 will cancel, and you're going to get b times s. Good? And then what you do is, since this has to work, see, I erased it, but this relation should be an equation between functions. So as a function of s, they should always give the same value. See, when I say this is equal to 1 over s times s plus 1, I'm saying that whatever the value of s is, they're always the same. Whether s is equal to 1, 2, 3, 4, 5, any value you plug in on the left, any value you plug in the right, they're always the same, right? So because this was inherited from the original one, which was A, like this one. This gave us this, and since this is supposed to hold for all values of s, this should also be true for all values of s. Okay? And that's the thing that we exploit. How do we exploit that? We are free to plug in anything to s, and that gives us the value of A and B. So I say s is 0. What happens then? This goes away, and A times 1 equals to 1, so that gives you 1 equals to A. Nice, right? Because that was exactly the value of A that we knew. Okay? And then you plug in s equal to negative 1. Why negative 1? Because negative 1 plus 1 gives you 0, deleting A completely, and you're just left with B. So that's why I chose s equals to negative 1. So you have 1 equals to B times negative 1, and therefore B is, for this to be a solution, B must be?
Negative 1.
Negative 1. And that's exactly the solution, right? Yeah. So if once you have that, you put it back, And what do you find? That was what we started with. So we did recover the original two fractions that gave us this. Okay? That's the basic idea of partial fraction expansion. Is that good? Are we still recording?
Yep.
Good, all right. So, back to our question. See, so what I'm trying to say is that there must be two fractions that would give us this. And, oh, by the way, there's another thing that I wanted to say. If you can factor this, then you should factor further, so that if it was like 3 factors, then you would have 3 fractions for each factors. Okay? But here, you can't factor this. If you try to factor it, you'll see that it doesn't work. So you're stuck with this. If you're stuck with this, then this is the best you can do. Okay? All right, now let's actually try to solve it. How would we find A, B, and C? I multiply this both sides. Okay, so
Just the denominator of the second one.
I'm going to multiply this to f. So think of this as an equation. This is equal to that. And I'm multiplying this to both sides. That's what I'm doing.
So you're not doing the bottom one?
This is the left-hand side. This is the right-hand side. Okay. So I'm multiplying this to both sides. So the left side and the right side. Is that good? Okay. On the left side, in this one, if I multiply this, what would I get? Negative s plus 10 times s plus 2. Because this one, when you multiply to this fraction, that part will go away, leaving you with s plus 2. Is that good? No? Not good? All right.
No.
Just-
Maybe rewrite the whole thing.
yeah, I'll just rewrite everything. Trying to rewrite this. See, if I had more room, I would be writing everything in one line, but because I don't have enough room, I just wrote it like this. But you should know, this is the left side, that's the right side, okay? All right, now we multiply what? S plus 2, s squared plus 8s plus 25 to every term that you see. Okay, for the first one, this cancels, leaving you with what? Now it's good. It's clear? Now it's clear, right? Okay, what about the next one? What do we get? We just get
13?
13. That's all we get, right? And then the second part, these cancel, leaving you with 8 times what? Yeah. By the way, even though I did this, please write it in this form, the completing the square form.
I thought it was just BS plus C on that one.
No, you need A over S plus 2 and B S plus 2 plus C over this. You need both, because this side has this and that. You need both terms. How can you create this if you only had that?
I thought that's what you wrote down before. That's what
No,
had.
I didn't.
Okay.
Okay, and then this and this cancels, giving you with B S plus 2. No, S plus, not S plus 2, sorry. This should be S plus 4, right? I'm sorry about that. Okay, so that's what we get after multiplying this thing both sides. And then we have to find A, B, and C. Okay, what should we do? Just give up, okay? Okay, what should we do? S equal to? -2 is a good choice. Because in that case, that becomes 0, you get 13. -2 plus 4 is 2. 2 squared is 4. 4 plus 9 is 13, so you get 13a. And then -2 deletes everything, so you get 13 equal to 13a, giving you a equal to 1. Nice. Okay, then what should we choose? -4 is the next best choice because that at least gets rid of this one, right? Okay, so let's see. That's -4, negative of -4 is +4. 14 times -2, that's -28 plus 13. And then -4 becomes 0, 9a. And that's 0, and that's C. And then -4 times +2 is -2. And because we know the value of 1, we can now compute this. This is -15. That's 9. And then -2c. Okay, if I move this to the, if I move it here and move that there, so I get 2c equals to 15 plus 9, that's 24. So c must be 12. And then to get b, there are two choices. One is you can plug in s equal to 0, just because. I mean, you just ran out of nice numbers to plug in. You can just plug in s equals to 0. That's one choice. Another one is to expand everything and do comparison of coefficients. Okay? Now, how does this work? Well, it's like this. If you expand everything and organize it term by term, just like how we compare the power series coefficients and set them equal to each other to solve it, right? You can do the same thing. You can expand everything, set the coefficients equal to each other. Now, that's going to take a long time. So instead of that, we can take another shortcut and say, well, I don't have time to do everything. Why not just look at the highest order term, pretending that you expand it? So if you expand this, it's going to be s squared plus something something, right? I don't care about the lower. I just know that s squared is the highest term. Okay? So this one will create as squared, so highest term. The first one will be as squared.
Is this to find B?
I still need to find b. That's why we're doing this. Yes. And then if you look at the highest order term, what is it? B times s. That's bs and then another s, right? So that's bs squared. And then you have on here. What do you get? Negative s squared. That's the s squared term. Right? So these are the highest order terms, and they should match. The s squared terms should match. So I know that a plus b is what? -1, making b as -1 minus a, and a, because a is 1, that's -2. Okay? So we got those values.
How do you know this one is 91?
Because
And now let's see what that ys is then. Y of s is 1 over s plus 2 plus b is negative, so it's -2 s plus 4 over s plus 4 squared plus 9 plus, and c is 12, so we get 12 over s plus 4 squared plus 9. So I just plugged it back in. Yeah. Yes? You have a question?
Yeah, on B.
Uh-huh.
Finding
What?
B. Can you explain what you did on the bottom there again?
Okay. Just expand the right side, expand the left side, compare the coefficients. If you expand the left side, what is this? This is negative s squared, let's see, 10, negative 2, plus 8s, plus 20, plus 3, that's 33. That's what you get on the left side, right? If you expand. On the right side, you're going to get a plus b, s squared, and then, what is it, 8s, 8as, 2b, and c. So you get 8a, 2b plus c times s, and I don't even know what the constant term is, okay? And what you can say is that a plus b should be negative 1, this should be 8, the constant should be that. That's what we're doing. If you expand them, the coefficients should match for them to be the same function. Yes?
Shouldn't the b term, or like the middle term, have c on it as well? Isn't it?
I split them into two.
Oh, okay.
Yeah, it's a b, s plus 4 plus c. So I split them into two. So do you get this? What I'm doing is I'm just saying that negative s squared should be same as that. That's what I wrote down here. Okay, if you expand the left side, if you expand the right side, for these two to be exactly the same function, that when polynomials, two polynomials are exactly the same function, if they agree for all values, then their coefficient must match.
Okay.
That's what we've been using all the time. Even for when we're solving power series solutions or Frobenius method, we wrote down one function, another solution, we set them equal to each other, and we said the coefficient must match.
Yeah.
That's what we were saying, okay?
Yeah.
All right, so now we have this result, and then all it remains is to look at the Laplace table to see which one corresponds to which. Okay, so that means y of t, what gives you this?
E to the
Negative 2t, right? That's number 2. Okay, and then the next one, it must be negative 2 times this thing. What gives you that? I think, let's see, it's in number 19. Number 19, it says, no, it's not number 19, it's number 20, right? So it says Laplace transform of e to the at cosine bt is what? It's s minus a over s minus a squared plus b squared. Okay, so if you match with this, so first of all, negative 2 is just some